Well, hi guys. This is a short video showing the automation setup for the 737 throttle quadrant, and just run through some of the modules here. So I've got the sides off of the module, and I'll just start on this right side, the first officer side. So this is how I set up the trim pot. It's a linear slider pot for the flap system, and when I move the arm, it likewise moves. I have this set up in a test mode now where the SIOC is just exercising various switches. So that's the slider pot off of an arm. It has a spring tensioning a cable that allows you to move this pivot arm, which in turn through the slot there moves the slider pot. This is the motor system. These are 6 RPM 12 volt right angle gearbox DC motors, and this module has a timing belt system with the poly clutch for controlling the throttle quadrant levers. The timing belt ratio is such that this potentiometer, which is a continuous 360 pot, is synchronized to go from full min to full max position of a rotation of 360 degrees. 340 degrees. So essentially it always gives the right pot value whenever the slider throttle slider lever is moved. Okay, and then over here I've got the parking brake set up. I used the same fixture as came with the throttle quadrant, and just simply replaced the bayonet bulb with a 12 volt LED version. So right down here is the mechanism, and I exercise it. This would be throttle lever off, throttle lever on. The micro switch is affected by the location of the rod. Inside the black piece there is a super magnet, and so the little cap screw here, steel cap screw, gets actually captured by the super magnet and therefore holds the brake lever up. Okay, here's another view of the TQ lever 1 gear motor and clutch system, timing belt system, and it likewise is synchronized so that from max value to full reverse equates to a given FSU IPC value, and that correlates with the SIOC code. Very similar to the TQ lever 2 setup. So this module rests nicely within the body of the throttle quadrant. The trim indicator is a servo-driven system attached to the 737 arm. And see if I can get down here. And there's the servo there. It's just a standard 322 high-tech servo, and it operates the trim indicator. Okay, so the fuel cutoff switches uses the existing micro switches, and I just tie into those switches, and it has a cam system, this little white nylon piece. So when the fuel cutoff lever is activated, it moves that accordingly. And in part of my SIOC code testing, I have a function where when I exercise the fuel cutoff, for example, it moves the speed brake handle just to determine its function. and the trim indicator moves accordingly. On the throttle levers, I've got the flap position set up so when it's in flap 5, then motors, the TQ lever motors are off. When it's in flap 10, it goes increased throttle. Flaps 2, it goes back to flight idle. Likewise, it's turning on the trim wheel motor, so I'll just demonstrate that briefly for you. So bringing the throttles back, trim wheel motors are going. Flaps 5, which was for the SIOC code here, is just demonstrating that the motor's cut off. Flaps 10, the throttle lever motors are active, moving it forward, and likewise the trim wheel motor is going in a reverse direction. I have the wired in also for SIOC control the horn cutout switch, which is I can use that for a reset or whatever. In addition, I have the stab trim switches set up to do some function, and I'm just seeing the activity based on the speed brake lever moving back and forth. Of course, manual control is had simply by overriding the clutch system. What else here? Oh, this is the speed brake lever, and when I move this back and forth here, you can see it actually functioning. All the trim, the speed brake functions have a delay to zero power for the servo, so it's not activating the servo when it finishes moving. The slider pod is located here, attached to the trim servo. Have a little Teflon block here that rests against the arm. This keeps it from actually moving laterally, which I found for whatever reason the mechanics being for the 737 tend to jog this around a little bit, so that keeps it from doing that. This is the high-tech, it's upside down, but 645 mg. This is a ball bearing servo. Produces about twice as much torque as the standard servo. So here are the electronics, the open cockpit cards, of course the DC motor plus card. I have the brake light function tied in here to the output side, essentially sinking current to light the LED. I'm feeding power to this via the 12 volts, positive 12 volts, into the center external plus 5 or plus V motors 3 setting. And the jumpers are set up for external voltage, and the quad jumper here is set for position 3. It's kind of a crazy arrangement they have, not well documented. Of course, the USB port. I chose to use a fiberglass, 3/16 fiberglass base plate. And essentially the length of this plate here is such that the main instrument panel module rests about here and then goes up and intersects at about this point here. So all this is enclosed behind the MIP, essentially aft of the CDU and lower ICAS unit. But it makes for a nice mounting of this. Here we have the DC motor card with its motor output arrangement. Here showing the position 0, 1. That's the trim wheel motor, and then the TQ lever 2 and TQ lever 1 motor. And these are various inputs for the switches, parking brake, and so on. Managed to find all of the switch locations from the existing wire in the 737 TQ. Just took a little bit of checking and testing continuity, but anyway, found those. By the way, on the output of, or the input of these, their convention is 0, 1, 2 through 9, although the PC board is labeled 1 through 10. Same with the outputs. Anyway, kind of screwy. Then likewise, they go here for the potentiometer inputs. They go from 1 to 8, but that convention is correct. So it's a little screwy. The documentation doesn't figure that out. Per the documentation, however, I do have the 10 microfarad electrolytic caps to dampen out the potentiometer fluctuations. That seems to work fine. So nothing else special on this. I bring power in, plus 12 on the left and plus 5 on the right. The actual current consumption of these is quite low, about less than 2 amps for the 12 volts and less than 2 amps for the 5 volts. Anyway, I decided to fuse these regardless. And this setup here is being powered by a PC power supply. So I chose to use a Coolmaster power supply, and I just took it apart and modified it so it could be used as a bench supply. I have here various disconnects for the plus 12 yellow and plus 5 volts and related grounds. Each has its own unique ground. In any case, that's the power. So I'll just do a quick rotation here so you can see the whole thing. Oh, I should show you the backlighting. All 5 volts standard incandescent bulbs within the TQ. And I'll turn the lights off to show you that real quick. Okay, and it's a nice effect. Okay, well, I'll end on that with the lights off and the backlighting shown, and all this is working nicely. Next step is to put it on the sim and plug in my values and parameters into Fred's code and see if it functions properly. That's it, guys.